Hey everybody, this is Marcelo Gleiser, and I'm really looking forward to this. This is our first session in English. My hope is that this is going to grow as it grew when I did this experiment in Brazil. It's still growing there. And the idea is very simple. All I want is to have a chance to talk to you directly about science, about questions you may have in science, and in related topics. So science and philosophy, philosophy here, of course, related to scientific questions, and cosmology and physics, and of course, any related issues to life in the universe as well. So I am here waiting to have questions from you. We have about half an hour or so. I see that there are quite a few people there. They are also very shy to ask questions. I see at least 43 people logged in right now, and I'm very, very happy to ask any questions. So my plan is to make this into a growing movement where I'm going to essentially cut off the middleman, and I'm going to have a direct conversation with all of you about questions that I consider interesting in science. Okay, so the idea would be to have you in these Q&A sessions ask me questions that you're interested in that could be about many different topics, like life in other planets, what's the Big Bang, how do we know the universe is expanding, what's the relation between science and philosophy, and there's a person who is asking me a question which is in English, but it's really related to Brazil. Mr. Amadeu Bego here is asking me what do I think about the Brazilian science and technology budget nowadays. And well, at this very moment, it's a disaster, and it's being cut down consistently. And I'm hoping that this is going to change as soon as possible. And of course, the plan is to touch on topics that you find interesting and that I find interesting. So, for example, I just watched with my kids, I just watched the movie Contact, which is based on the novel by Carl Sagan, which is really about the search for extraterrestrial intelligence program, which has been going on for over 50 years, with the idea that you'll be able to listen to potential radio sources, radio signals coming from extraterrestrial civilizations that, just like us, developed some kind of technological way of communicating via radio waves. So the same way these radio waves are moving out of our planet, the radio waves will be moving out of their planet, and hence we should be able to capture them here on Earth with our radio telescopes, and perhaps confirm the existence of intelligence in other worlds without having to go there, right? Because having to go there is extremely complicated, because interstellar travel is pretty much impossible, at least for us right now. So since nobody's asking questions, I'll keep talking about this topic because it is a very important one. And the idea of interstellar travel is really related to the very, very huge distances between stars in the universe. So the closest one being Alpha Centauri and Proxima Centauri, closest to the sun, 4.5 light years away. That would take 4.5 years for us to get there, traveling at the speed of light, which we don't. So if we actually use our fastest spaceship to get there, say, 30,000 miles an hour or so, it would take us about, give or take, 100,000 years. So 100,000 years is a freaking long time. And that's one of the reasons why we can't go to other stars yet, right? Now, we have a question here. And there is a question about Sagittarius A. Sagittarius A is really related to the possibility of having a black hole there. We already know there is a black hole there, right? And we know that it's towards the center of our galaxy. And so that's one of the things that we are doing. We're looking at the center of the galaxy to look at how stars are moving close to this black hole. And we can infer the existence of this black hole just by the way the stars are moving. It looks like you have a very small source of gravitational attraction. And so that with a huge power. So the only way you can concentrate that much power in such a small volume is if you have something very compact. And a black hole is by far the best and perhaps the only explanation we have for that. Let's see, add something else here. Do you think that quantum computation can help in astrophysics studies? I would like to know if they use quantum computers at CERN. So as far as I know, they do not use quantum computers at CERN yet, because first of all, building them is still in a very preliminary stage. Turns out that the big leader in quantum computing right now is actually Google. One of the big leaders anyways is Google. And the quantum computers can only do certain kinds of tasks, and they are not yet adapted to the kind of computation you need in particle physics, like at CERN, the European Laboratory for Particle Physics. But this doesn't mean that it can't happen in the future. And in fact, quantum computation is going through a huge expansion right now. And as soon as we have ways in which we can use optical switches to make these quantum computers work fast enough and reliably enough, then I believe that it will be a matter of a few years before we can actually start applying those machines to research, not just in astrophysics, but in particle physics and engineering and many, many other fields as well. Okay. Okay. So somebody's asking me about the multiverse, right? So that's always a great topic, and it's a very popular topic. And the idea is the following. As we know, right, everything that we have here in this universe, all the galaxies, even though they're expanding away from one another, they are within what we call a universe, right? And that would, by definition, mean everything, every state of matter that exists is contained in this universe. However, there are certain theories of physics that predict the possibility that our universe is not the only universe. There could be other universes out there. They are motivated by the sort of a dream that theoretical physicists have, that Einstein had, and he worked on this for like the last 20 years of his life, that all forces of nature are actually manifestations of a single force, a unified force. And this unified force, if it existed, would be, at least in the theories that we have now, for example, one of them, the most popular one, is called superstring theory. And that theory says that in order to enable these four forces to become a single force, you actually have to work in a universe that doesn't have three physical dimensions, north, south, east, west, up and down, but it actually has 9 spatial dimensions. So 6 dimensions on top of the three that we move around, right? And the question is, where are these things, right? And the idea is that they tend to be very far away, the same way that if I grab, for example, this hanger here, right? And you look at it and you can see that, this line here is not really a line, is actually made of a 2-dimensional. It's really a very, very elongated cylinder. But if I start moving this thing very, very far away, you're going to start looking at this in more and more like if you were a 1-dimensional object. So only when you're very, very close to it, that you can really see that this is a very elongated cylinder. So the idea is that we don't see the extra dimensions because they are super tiny. But if we could probe them very close by with very high energy physics, then you actually see these extra dimensions. So the question becomes, all right, so if there are 6 extra dimensions, what kind of shapes they have, right? Well, we don't know, but there are many, many theories about this. And one of them is that they could have shapes, 6-dimensional geometries, they have different topologies. And if they have different topologies, they could have different minima, so to speak, where one kind of universe with a different 6-dimensional internal space is realized and another one with a different 6-dimensional space is realized. And when you look at that from a 3-dimensional perspective, what you have is what's called a multiverse, where, at least in string theories, you call this the string landscape, where you can have many, many realizations of these 6 dimensions that would imply that these universes with different topologies in 6-dimensional space would actually have different physical properties. So, for example, if the electron has a mass and a certain electric charge here, in another parallel universe, it could have a different value. And so we have this multitude of potential universes out there. We can't reach them. They can't reach us because they are outside what we call our cosmic horizon, the distance light could have traveled since the Big Bang. But they potentially exist, and they could have different laws of nature applied to them. So that's, in a very, very small nutshell, is what we call the multiverse. And one thing that I want to say is that I'll probably start preparing short, like 15-minute long lessons soon enough. And I'll post them on the YouTube channel that you're watching. And I'm going to have those lessons be live. I'll create an event on YouTube live for these lessons, and you will be able to watch them, and we'll have a Q&A right afterwards. And I'm sure that one of them is going to be about the multiverse. Okay, so let's see if there is anything about something that, if one person here is asking me if we, the human species, is still evolving, right? And this is a very interesting question, because I was just in an event with an anthropologist a couple of weeks ago, and somebody in the audience asked that same question. And he said, "Oh, I love this question because the answer is yes." So it turns out that some people are beginning to lose their molars because they don't use their molars anymore. The canines are not as sharp as they used to be. And there are all sorts of different issues in how we metabolize certain kinds of food that we don't need to metabolize as well anymore. So at this level, yes, humanity is still changing very slowly given the theory of evolution by natural selection. But of course, there are different ways in which we're changing, which are much faster than the theory of evolution, through medicine and through our interactions with the environment, with one another. There is something called epigenetics, which is a different kind of change that can happen at the genetic level, where people react to stress in different ways, and those reactions can actually be carried from generation to generation, not permanently, but for a while. And hence, those things are happening too. And of course, eventually, we're going to start interacting directly or acting directly on our genetic code, and we are going to be the ones that will be changing the way we look and the way we think and the way we operate in the world. So this sort of like cyborg event is going to happen, and in a sense is already happening in different ways, by the way we interact with, say, cell phones, with machines that extend our existence in different ways. But I'll reserve that for another time. Okay. Let's see here. What else? So one of the questions is, do you think quantum field theory is a complete explanation of nature? And the answer is no, I don't. I think that quantum field theory is a wonderful device that we have developed, and that explains very nicely what we know right now of particle physics, in particular how particles of light, photons, interact with electrons. That's called QED, quantum electrodynamics. We also have QCD, which is how quarks interact with one another, and particles called gluons to create protons and neutrons, and also particles which are called mesons. But I think we are far from getting to the end of the story. I would say that quantum field theory is a work in progress. There's a lot that we still don't understand. Normalization is a technique that we use in order to be able to calculate the probability of scattering, like two particles come together, where they're going to go and what is the intensity of their scattering, the amplitude. And we calculate things, and in order not to get infinities, we use techniques from quantum field theory. But clearly, there is much more to this than we have done so far. And of course, one of the big questions is, how do you include gravity into that scheme? I mean, gravity, as far as we can tell right now, does not seem to like quantum field theory very well. You can't really calculate things properly. And the superstring theories that I mentioned before in the context of the multiverse is one potential candidate to include gravity in a quantum field theoretic approach. But it's not the one that is finalized at all right now. I mean, we're somewhat stuck in some ways in string theory, at least when it comes to applying it directly to the real world, right? And there is also something called loop quantum gravity, which is another way in which you create a universe, a space which is made of linked little loops, which are sort of the quanta of space and time, and they essentially make gravity into an emergent property of this linked space and time. And of course, there again, there's a lot of progress to be made. So I would say that quantum field theory, like most theories in physics, is not a done deal, but is a work in progress. So one person here is saying, what book would you recommend to comprehend quantum physics? Well, it depends on what level you want to study quantum physics, right? If you want to study quantum physics at a non-mathematical level, so just a description of quantum physics, I have to say that my books, The Dancing Universe, which in Brazil is called A Dança do Universo, and my book, The Island of Knowledge, A Ilha do Conhecimento in Brazil, both of these books do a great job, I hope, at least I tried very hard to convey the basic fundamental questions and concepts of quantum physics without any mathematics, right? However, if you want something a little more mathematical, but just introductory, I would suggest you read volume 3 of the Feynman Lectures on Physics. So the Feynman Lectures on Physics is a book, it's a collection of 3 books of introductory physics. In volume 3, he goes into quantum physics, and he is a fabulous, brilliant expositor, and I think you're going to like it. And it does have math, but it's basic math, but it's a good way to start. Okay, let's see. Okay, let's see what we have here. All right, I have another question. Can gravitational waves give us some evidence of cosmic inflation? And the answer is absolutely. That is one of the big hopes for gravitational waves, is that, so cosmic inflation essentially is a period in the history of the universe, very, very close to the Big Bang, when the universe expanded very fast, exponentially fast. And because of that, it basically stretched everything. And there were lots of fluctuations in the so-called fields that filled up, the fields of matter and the field of gravity that filled up the universe. And those fluctuations, they create an imprint that is sort of registered in the universe, and in principle can be measured as a stochastic, a background gravitational wave in the universe as a whole. It's one of the signatures is because there was this big stretching of space in a small amount of time, those waves are very flat across different frequencies. So you would see a very clear signature of that. We don't have detectors that can do that yet because the amplitudes are weak, but it's not a no forever. It's very possible that we're going to have that. And there are other more complicated signals that have to do with something called tensor to scalar ratios, in the way particles, fields behaved, and those have an imprint which is also gravitational, and that is related to also the microwave background, and there are imprints in the microwave background that in principle carry this information about the gravitational behavior of different fields in the early universe, and those things can also be measured. So yes, that is a possibility indeed. Okay. Okay. Okay, one person is saying, why does gravity give acceleration to other objects? So I assume that this person, Batista is his name, is asking about what's called the slingshot effect, which is essentially is that used very much in space traveling, where you have one rocket ship approaches a planet, gets accelerated by it, and goes out. And by doing that, is accelerated, the gravitational field accelerates it. And it's very much like if you are falling down a slide, right? That doesn't stop at the ground, but that keeps going. And you get accelerated on your way down. And so if you can go straight without friction, you're going to gain speed by doing that. So it's a very similar idea, but applied to orbits of planets. And that's how you get space probes traveling to different worlds and very far away worlds without using a lot of fuel. You use the gravity of a planet in the way to accelerate them that way to other places. Okay, so that's the idea. Some people are saying that I'm having issues with the video. Not sure exactly what's going on. Is the video better? Okay, the video is not getting any better. And I think because of that, and because we already have 20 minutes or so, I am going to stop. It is just some sort of interference. I have no idea why this is happening, but I'll make sure that in the next one, we'll have a better view. Okay, guys? So thank you so much for watching. It's about 20 minutes of video and conversation, and I'll come back very soon with another Q&A, and hopefully we won't have this green light. Maybe aliens are coming into my room. But it's good to meet you. It's good to listen to you. And let's make sure that you tell your friends that this is happening so that I can get more people to ask great questions about science, the universe, philosophy, and everything. Thank you so much for watching, and see you soon.